everyone. Welcome to episode number 632 of this here electronic engineering podcast called Amelia's Weekly Fish Fry, brought to you by eejournal.com and written, produced, and hosted by me, Amelia Dalton. Battery management takes center stage in this week's Fish Fry podcast. My guest is Danielle Chu from MathWorks, and we explore the primary functions of battery management systems and the common challenges faced by engineers when designing these types of systems for electric vehicles. We also investigate the role that modeling and simulation play in battery management design, the importance of cell characterization for battery modeling, and how MathWorks is encouraging innovation in this arena. So without further ado, please welcome Danielle to Fish Fry. Hi, Danielle. Thank you so much for joining me.
Thank you so much, Amelia, for having me here.
Absolutely. So, Danielle, let's talk about battery management systems. Now, first, what are the primary functions of a battery management system, and what challenges do engineers face in designing these systems for electric vehicles in particular?
So first, let me start with a battery management system is very critical to monitor and manage the battery pack's performance and health. So without an effective BMS, negative outcomes can arise. For example, overcharging, excessive heat generation, and which could cause thermal runaway and fires. A BMS provides 7 primary functions. First, monitoring. The BMS continuously monitors the voltage, temperature, and current to make sure that they operate within safe limits. Second, protection. BMS provides the safeguards against conditions that could harm the battery, such as overcharging, overcurrent, and overtemperature. So protection actually prevents the battery damage and ensure our user safety. The third primary function is cell balancing. So over the time, the individual cells within a battery pack will exhibit different charge levels due to variations like in manufacturing, usage, or temperature conditions among the cells. A battery management system, so they balance the charge across the cells to ensure that all the cells have the same voltage, the same charge level, so that it can maximize the battery's capacity and lifespan. And the fourth important function of BMS is state estimation. It estimates the key metrics like state of charge, state of health, and state of power, so that it can tell you how much available charge remaining in your vehicle and what's the mileage available for you to drive. And the fifth function is power management. The BMS oversees and controls the power flow to and from a battery pack. So for example, during charging, the BMS prevents overcurrent and overvoltage. Thermal management is another important function. That controlling the temperature is important in batteries because high temperature significantly decrease the battery life, and the lower temperature will lower the useful capacity and energy. That's why in the winter, my electrical car has less mileage compared to in the spring. So the BMS activates heat or coolers to keep the temperature within safe limits. Last but not least is the communication. The BMS communicates with the external device or systems, providing the real-time information about the battery status and receiving instructions for energy management.
So, Danielle, talk to me about those challenges as well.
Okay. Quite a few challenges that engineers encounter when designing a BMS for electric vehicles. First one is the accuracy and reliability aspect. As I mentioned, the BMS provides state estimation. So the BMS has to make sure those state estimation, like state of charge, is accurate. So it provides accurate estimation of the mileage of the electric vehicles. drivers can rely on those data estimation. The second challenge, which is the thermal management. Engineers need to design the systems that effectively manage the heat inside the battery packs to prevent the damage and ensure the user safety. So we are aware there are a lot of safety and compliance standards. Engineers have to design systems that meet those safety regulations, which make designing the battery system more complex. Last but not least, the cost and faster development time. The electric vehicle market demands faster development time to keep pace with the technology advancement and consumer expectation. So the consumers expect a quick quick launch time of the new generation electric vehicles and more cost effective.
So, Danielle, let's also talk about modeling and simulation here. Can you talk about the role that modeling and simulation plays in BMS design and which aspects of BMS design could benefit the most from early stage simulation?
Sure, I can talk about the workflow of the modeling and simulation playing a role in BMS design. MathWorks provides block diagram that lets engineers perform system-level multi-domain simulation, which includes electrical, like the electromotors, mechanical, and digital control, like the algorithm, BMS algorithm itself. So that running the system-level simulations, engineers can understand the interactions within the system. So by running these system-level simulations, engineers can understand the interactions with the systems. Then next, engineers use Simulink to model the powertrain of an electric vehicle and use MathWorks optimization toolbox to identify the battery size so that the electric vehicle meets the range and the cost targets. So once you know the battery size, you can use a toolbox like SimScape battery to model your battery pack and BMS algorithms like state of charge estimation, cell balancing, and so on. And the same Simulink models can be used to generate a C and HDL code for hardware in the loop testing to further validate the BMS algorithm in real time. So you generate the code from battery model and deploy the code to real-time target machine, providing a virtual real-time environment that represents the battery pack, active and passive circuit elements, the loads, the charges, and other components as well. So this virtual environment lets you validate the functionality of the BMS controller in real time before developing a hardware prototype. And based on the real-time simulation results, you can verify and refine your BMS design, iterative process. For example, you may go back to change the state of charge estimation algorithm in the models, regenerate the code, and test again on hardware in the loop. So by the time engineers go to actual hardware testing, the algorithms are more mature. So engineers spend less time on testing with the real hardware.
So, Daniel, also talk to me about the aspects of BMS design that could benefit the most from early stage simulation.
Sure. As I mentioned, that I can talk some specific benefits that BMS design can benefit from any stage simulation. First, engineers can use open loop desktop simulation to validate the logic of the BMS algorithms implementation before deploying them in real-world applications. For example, is the cell balancing algorithm activated when the cell voltage are unbalanced and meeting the threshold? Is the charging control logic implemented correctly? So these can be tested using open loop desktop simulation. Second, BMS design needs to meet a set of requirements, like I mentioned before, the accuracy of the state of charge estimation and all the different conditions, overcharging or overheating protection as well. Engineers can test the BMS algorithms using closed-loop desktop simulation with a battery plant model to make sure the BMS is designed to meet all the performance requirements. Third, There are a lot of control parameters need to be tuned in the BMS algorithms, and desktop simulation provide quick feedback for tuning the BMS algorithm parameters. The fourth, engineers also use desktop simulation to explore different design choice and evaluate the trade-off between them before committing to a hardware prototype. For example, engineers can use a simulation to evaluate different balancing configurations. Should using the active balancing or passive balancing? And if using passive balancing, what's the optimal resistor value? And fault simulation helps identify potential safety risk and develop a strategy in the BMS to detect, respond, and mitigate them more effectively. Otherwise, the battery in electric vehicles can be very dangerous if they fail. So, for example, engineers can inject the non-intrusive faults inside the battery, such as open circuit due to the defects or disconnection or short circuits or even thermal runaway. So understanding and addressing those potential faults early in the design phase can help reduce costs associated with recalls, repairs, and warranty claims. Another one, the benefit is electric vehicle must meet functional safety and compliance standards, such as ISO 26262, and software like Simulink supports automatic code generation, ensuring that what is tested in the model is what runs on the hardware. And the generated code can be configured to comply with automotive coding standards, such as MISRAC, which aligns with ISO 26262. Last but not least, another benefit is the BMS does not run alone on electric vehicle. As mentioned, that it has traction motors, cooling systems. So engineers can run the vehicle level simulation to study how different components of the electric vehicles, such as the battery, electric motor, power electronics, and the BMS interact with each other. So it helps in identifying integration issues early in the development process, reducing the risk of costly redesign. And engineers can also simulate different driving scenarios to optimize energy efficiency and the vehicle's range.
So, Danielle, what is the importance of cell characterization in battery modeling, and how can engineers use cell characterization to fit a battery model to experimental data?
Sure, the cell characterization is the process of fitting a battery model to experimental data. Accurate cell characterization is important because the BMS algorithms use the battery model to set control parameters, such as the common filter covariance for the SOC estimation, or the power limits based on SOC estimation, or even the temperature to avoid the undervoltage or overvoltage conditions. That's why it's very important to make sure that the model is very accurately reflected the experimental data. However, successful cell characterization, engineers should follow a structured approach, and the steps include data collection, model selection, parameter fitting, and validation to make sure that the battery models reflect the experimental data correctly. Here are the specific steps. The first is data collection. Engineers need to decide what test to conduct in the battery test lab and collect the data on voltage, current, temperature, and sleep charge during the charge and discharge cycles. The second step is the battery model selections. Engineers need to choose an appropriate battery model that can be parameterized to fit the experimental data. And the choice of the battery model affects the complexity and accuracy of the simulation. The battery equivalent circuit model is often deployed for BMS design because of its simplicity, high fidelity, and computational efficiency. The third step is parameter fitting. So once selected the battery model type, then engineers using techniques such as curve fitting, optimization algorithms, or machine learning to adjust the model parameters to minimize the difference between the model's predictions and the experimental data. Precise parameter fitting ensures that the model can accurately predict battery behavior and a wide range of conditions. The fourth step is validation. Engineers need to validate the fitted model by comparing its predictions against additional sets of experimental data, maybe using a drive cycle current profile. And this data must not be used in the fitting process. It should be a new set of data. The last step is iterative refinement. Based on validation results, engineers may iteratively refine the model by adjusting parameters or incorporating additional data to improve the accuracy.
So, Danielle, can you share some examples of use cases where modeling and simulation have enabled faster development cycles and reduced costs in BMS design?
Sure, we have been working with the customers on this subject. One example is engineers can use simulation tools for system-level multi-domain modeling to understand the component interactions and evaluate the design choice, like different battery pack configurations affect vehicle range and energy consumption. Multi-grain proportional labs build a system-level simulation model of the vehicle. Use it to test how different components work together and validate the designs earlier in the development cycle. Simulations let them test concepts quickly and easily iterate to refine the BMS design. Another use case is where engineers use simulation to develop and test different BMS algorithms with the battery plant model. One functionality, as mentioned, of BMS is cell balancing, which ensures all cells in a battery pack have the same state of charge. Without balancing, some cells may degrade faster than others, reducing the capacity of the battery pack and driving range. Engineers at Green Tiger Mobility simulated real-world conditions and selected the appropriate balancing resistor for cell balancing and determined discharge currents involved. They mentioned that the simulation streamlined battery pack development and robust BMS design, resulting in time and cost saving. One last use case I'm giving here is the electrical vehicle market demands faster development time to keep pace with the technological advancement and consumer expectations. Engineers use simulation software that allows early validation, easy debugging, rapid prototyping, and testing of components and systems in a virtual environment to reduce the time needed for physical prototypes. For example, Exponent Energy accelerated product prototyping through code generation from models, rather than debugging C code for the application and drivers. Just 3 engineers were able to complete the 400 volts fast charge in only 10 days, and despite none of them being firmware experts. They accelerated the development, testing, and verification of the entire solution by at least 5 times. So using simulation, engineers may spend more time upfront on the simulation, but the testing on actual hardware will be likely more successful and quicker. And at the end, the development cycle is shorter and cost is reduced.
All right, Danielle, it is time for your off-the-cuff question. So if you could have one meal right now, it doesn't matter if it's on the other side of the world, you need a passport to get there, what would you have?
If I could have any meal right now, I would love to travel to Dongao Island, a former small fishing village in Guangdong province, China. I would like to sit in a seaside restaurant, enjoying the freshly caught seafood, different fish, crabs, and many shrimp, and all prepared using the Cantonese cooking methods. I had that back more than, I think, 10 years ago. So
Ah,
if I could have that, I would like to go back
I
to have
love
the same
that.
thing.
I love that answer. Wonderful. Well, Danielle, this was super cool. Thank you so much for joining me.
Thank you so much for having me, Amelia.
If you'd like even more information about this topic, I've included a couple links below the player on this week's fish frying page on eejournal.com and in the description for this week's YouTube episode as well. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EEJournal. If LinkedIn is more your thing, I dig it. You can follow us or me on LinkedIn as well. And we are also on Blue Sky Social and Mastodon too. And we have a YouTube channel, youtube.com/EEJournal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series, hosted by me, and our new animated series called Libby's Lab. And of course, you can subscribe to our EE Journal YouTube channel as well. Also, make sure that you subscribe to this here podcast on Spotify, Podbean, Apple Podcasts, YouTube, or just about any other podcasting platform to listen to some exciting upcoming episodes. Thank you everyone for tuning in. If you know of any cool new technology or heck you just want to chat, shoot me a line at Amelia, that's Amelia, at eejournal.com, or post a comment on our forums on EE Journal. For the week of May 16th, 2025, I'm Amelia Dalton, and you've been fried.